Okay. So I will start. So today's presenters are me and Yifan will be here later soon. So I will just start the presentation, and today I'm going to talk about detailed rigid body simulation with extended position-based dynamics. So yeah, I will start. So these are the outline of today's presentation. So I'm going to talk about just general physics simulation for the robotics, and then I'm going to get into the main topic, which is the position-based dynamics, and then conclusion. So okay, so physics simulation for robotics. So we know that a lot of robotic scientists use physics simulation because it might not be perfect, but it's very useful because it's cheaper and safer than the actual environment. It's a good environment to test out the robots and algorithms. And you already know like some physics simulation for robotics, such as gazebo or pipelet or Musoko or something like that. So we're going to briefly just look at their differences, and we're going to look into a physics model called position-based dynamics, which specializes in non-rigid object instead of rigid objects, but we can also deal with non-rigid objects. So today there are like multiple physics simulation you can find, but we're going to mainly talk about physics simulation that can deal with the robotic arms, and which usually has a pipeline as below. So first you calculate or simulate the force such as gravity, and then you check the constraints and resolve the constraint. For example, constraint can be a joints constraint, or it can be a spring damper constraint, or it can be any collision constraint, something like that. And then you update the position and the velocity of the rigid body or the particle object, and then you repeat that process while rendering the object based on the position and velocity. So there are multiple criteria you can differentiate different physics simulation. For example, there are different physics engine. So ODE is a physics engine, Bullet, Physics X, Musoko, they're all physics engine. And you can create a physics simulation based on those engines. For example, Gazebo is based on the ODE, and Pybullet is, of course, based on the Bullet. And some game engines, such as Unreal Engine or Unity, is usually based on Physics X or Bullet, something like that. And Musoko, they have their own physics engine based on their own calculation of contact physics. Yeah. So those are one criteria of choosing the physics simulation. The other criteria is this is more like a recent thing, but we can differentiate by a differentiable physics simulation or non-differentiable physics simulation. The four physics engine I just mentioned are all non-differentiable, but nowadays they're making a differentiable physics engine called BRAX, which is based on position-based dynamics, and written in using a language called JAX. And Dozo is a differential physics engine based on the velocity-based dynamics, force-based, and it's written in Julia, and it has a wrapper for the Python, and the differentiable collision detection that Chi last time talked about is actually from this Dozo, and every process in their simulation is differentiable as long as the objects are complex. And then another criteria for differentiating the physics simulation is what kind of formula it is based on, like physics formula equation, such as there's an impulse-based physics simulation, physics engine, and there's a force-based physics engine, and there's a position-based physics engine, and the four mentioned before are all force-based physics engine. But today I'm going to talk about the position-based physics engine and why do we have to use it even if most physics engine are force-based. So I'm going to talk about those reasons carefully.
Quick question. Differentiable you mentioned is only dojo and brax and not the four at the top.
Yeah.
ODE like appears to be differentiable equations. So
No, that
solve
name is not
solver
that
is-
OD. It's just physics engine's name.
Oh, it's not only differentiable.
Yeah. It's
Oh,
a physics
damn.
engine. So it's different
Got it.
thing. Yeah, but gazebo is based on the ODE in physics engine. And different simulation are based on different engine, or they make their own like Bozoku. So yeah, that's why we're getting to this position-based dynamics. So yeah, these are the equation or the pseudo algorithm for force-based physics simulation and position-based simulation. So force-based physics simulation is basically based on the F equal ma, which you guys already know of. So basically, you initialize the position, velocity, and the force, and usually the inverse mass. And then you calculate all external force and add them up in the original force of the object. And then you resolve the constraints by resolve the constraint by solving for the force that will resolve the constraint. And then you add them up and you apply the F equals ma, and then you integrate the velocity, and then you integrate the position. The other part is the position based algorithm, pseudo algorithm, which doesn't have an initial force, but you calculate the velocity and you calculate the temporary position, and then you solve the constraint based on the position, not the force. And then you calculate the new position, and based on the difference between the temporary position and the result position, you calculate the velocity. So these are the fundamental difference between the two different methods. And for accurate force calculation, of course, the force-based physics and dynamics is more accurate, but this position-based physics engine is more stable because you calculate the position right away instead of integrating the force. So for example, if some object is penetrating the environment, which is a collision case, this resolves by adding a force, repulsive force, back to the non-empty space of the environment. But it will not be, I will say, will not be instant. So basically, it takes some steps to actually resolve that collision. So this sometimes overshoots or is unstable. So I'm not sure if you guys all have used some velocity-based physics engine, but when you have a lot of collision in this kind of simulation, you have a kind of a shaking object. Object is like shaking and very unstable. But position-based dynamics doesn't have those kind of shakes because you're resolving the position right away instead of the force. So it is less accurate, but it is more stable. So when you're trying to simulate the non-rigid objects or bunch of particles, this tends to be more stable. So yeah, so velocity-based method is what most of simulators use because it's very accurate, and it's really good at dealing with the contact physics, but it overshoots sometimes and creates some shaking. So, but we'll look into position-based method because many human-robot interaction scenarios, we have a lot of non-rigid objects actually, like even human is non-rigid object that can be flexible, or any and many objects in the real world is not non-rigid objects. So in order to simulate those kind of things, this position-based method is way better than the I will not say way better, but it's usually better than the velocity-based method.
Accuracy is compared to the velocity.
Accuracy compared to the real world physics. Real world physics. Like how does it act? Like, for example, if you push the box, it will on the table, it will create a friction force that kind of shifts the box's movement, right? So if you run the velocity-based physics, then it is actually it kind of mimics the position and also velocity and also the force that is acting on that box. But for position-based dynamics, it's less accurate than that if compared to the real world. So yeah,
Quick question.
especially force calculation.
So, the two forms can be, I mean, two kinds of simulators can be interchangeable because you have momentum in one and you have force in the other. So momentum can be used to calculate the force.
I will talk about it.
Okay.
Yeah. So this is the position-based dynamics. This is from the previous work of the paper that I'm going to talk about today. So basically, you have an initial position and some multiplier, and you solve for every constraints, and then update the position, and then based on the updated position, you update the velocity. So and then how you calculate this updated position and then updated lambda is as like this, which is very simple. So yeah, it is very simple. So you get a lambda based on the inverse of this, and then you just matrix multiply, and you get a new position. So that's how you resolve the constraint. But the problem of this was
sorry to disturb you, Hojin. Could you use the mouse cursor to show the lambda and everything? I'm not really able to follow.
okay.
Annotation, I think, is there.
Yeah, that's much better. Thank
I
you.
just explained this. Now I was just saying that this equation can solve this part, solve the constraints here.
All right. Okay.
Yeah, it's pretty much straightforward. But the problem of this is only for the non-rigid simulation and the particle simulation. It was not for the rigid body simulation. It doesn't have an orientation, or it doesn't have a rotation, or it doesn't have a friction. It doesn't have a collision, well-defined collision for the rotation. So the work that I'm going to talk about today kind of resolve all these problems and more physically accurate compared to the previous work. Yeah, so that's what I'm going to mention. So this is the new pseudocode for this position-based rigid body simulation. So first, there are three improvements. One, they speed up the convergence speed by using a thing called substeps. And second, they extended their algorithm to the rigid bodies, and they combine actually the position-based dynamics with the impulse-based dynamics. And also they listed out like how to implement different kinds of constraints. So these are the constraints in below, these are the constraints in below. And then if you look at the algorithm here, basically you have so the iteration is iteration of the solver. A substep is actually dividing up the time step into very small things, and then repeating this whole thing instead of just repeating the solver. And actually, they found out that you just need even with just one solver iteration, and with a lot of substeps, it actually creates better result than having a many iteration in the solver. So that kind of sped up the convergence speed, and it is pretty fast compared to the velocity-based dynamics. And then if you look at here and here, you can see that they also integrate the rotation of the object, which is based on the torque and the inertial metrics. Yeah, so that's how they improved the thing, and this became very physically accurate compared to the previous. It might not be as accurate as the velocity-based method, which calculates the force right away, but this kind of gives very good results also. So I'm going to quickly talk about the constraint. I'm not going to talk about everything, but I'm going to talk about positional constraint and an angular constraint, which is the base constraint for all other constraints you can do. So yeah, this is the position constraint. The left is the position constraint, and right one is the angular constraint. So here's a lambda, which you already saw from the previous work. So it is pretty much the same thing. It looks very difficult, but it's actually not very very hard thing. So basically, they update the position based on this lambda, which can be calculated with the first two. Those are just inverse match. It's just inverse match, and then just calculate the lambda, and then just update it based on this equation. And then using an impulse-based dynamics, you can calculate the force in this way. And for angular constraint, it is the same thing, except it is you calculate different inverse mass, and then update the lambda based on this equation, and then update the rotation quaternions like this. And then when you calculate the torque, you again use the impulse-based dynamics to calculate the torque. So yeah, these are the base things. So if you have a joint constraint, which is, let's say we have a rotation joint, then we have a angular constraint and then also some kind of a position constraint. So you just have to add them up and resolve the constraint. And those constraints are well written in this paper. You can, yeah. And I forgot to mention that this paper is from the SIGGRAPH conference, which is the computer graphics conference. So this was originally created for realistic computer graphics, but yeah. So that's why they try to make it as stable as possible, because they have to render very realistic movement in such as animations. And then another thing they added was the velocity update, which was not in the previous work. Basically, when they do a velocity update based on the position, change position, they also do a one more iteration, which resolve the friction and the restitution. Basically, those are dependent on the velocity. That's why they have added one more iteration for those friction and restitution. And this are the equation. It looks complicated, but it's actually not that complicated. So that's how I resolve it. So that's something they added here. So yeah, so I will just show you what is the result of using that thing. So I will show you the simulated result, but this was ran in the CPU, not using a GPU. And this position-based dynamics can be easily parallelized compared to the velocity-based dynamics. So I will just show you the video. So yeah, this one is demonstrating the joint constraint and position constraint. This is demonstrating the non-rigid movement of the objects. Basically, this has a, what is it? The spring. It's a spring damper system. So you can do very unique movement that you can see from the real world, which is rotating the string. You know, when you rotate the string, it kind of swerves by itself. It's showing that. And this is the one that combined the rigid body dynamics with the non-rigid body dynamics. They have a spring that is non-rigid, and they have a tire that is non-rigid, and everything else is rigid.
How they model the sand, like a rigid surface, it looks like.
I guess it's just a plane. I think it's just. So this is the simulated result. So you can see that there's a bounce in the tires, but other things remain rigid. this was running CPU. Maybe one more thing. And this is showing that how fast it is. So you can simulate multiple moving objects, such as these marbles. And this is easily parallelizable. And this is running in CPU. So there's by this, they're saying that it is fast and accurately mimicking the rigid body movements. Yeah. So. Yeah. So I will go into the conclusion. So first, using this position-based dynamics might not be good for the robot arms itself, but for simulating the objects that robot interacts with, such as this clothes or some kind of a liquid or some human body, this position-based dynamics works well. And even the differentiable simulator, the Brex, also use the position-based dynamics. And also NVIDIA Isaac Gym combines, actually they used all, they combine velocity-based dynamics for robots, force-based, I mean, and then use the position-based dynamics for non-rigid objects. So they use both at the same time. So I think it is good to know this position-based dynamics if you're trying to do a HR scenario that involves some very non-rigid objects, such as like cooking. And another thing you can learn from this is that this position-based dynamic can be easily made differentiable. So you can do a very cheap physics-based optimization. So the image below just shows how you can use this physics simulation to optimize the hand pose of grasping different objects. So bottom one is the result of the optimization. So in order to get these grasp poses, they just it takes a little long, which is about 10 seconds for one grasp pose. And if you use a GPU, you can get faster than that. But still, so you can see that compared to the one in the upper, compared to the upper ones, it can create more content-rich grasp poses. So they're using also position-based dynamics. So if you want to do some kind of optimization based on the physics equations, then you can try to run this differentiable physics simulation and then get those kind of results. Yeah, so I thought that this might be useful for everyone's project. So yeah, so this is all. And if do you have any questions about this? Yeah, do you have any questions?
Position-based dynamics is good for the deformable objects, like
Good for the deformable objects or particles.
similar particles.
Yes. If you have a lot of objects, that's hard to.
You go back to the slides where you have the pseudocode for philosophy. That also.
Yeah. This one. Yeah. So
If you use the position-based simulation, how do you drive the objects? You need to introduce force to drive the objects.
you can add an external force before running the velocity here. Yeah. And if you look at the actual pseudocode, you can see the external force and external torque here, and then update and solve for the position and then update it, and then solve for velocities again down here. So yeah, you can deal with the external forces, but because it's calculating the force and torque kind of later instead of directly calculating the force like this, the force calculation is not accurate as the force-based dynamics. So if you want to do like, for example, torque control, force control of some object, then position-based dynamics might not be a good choice.
Just curious, difference between the deformable and the non-deformable is going to be elasticity. So is it like that some like elasticity value between 0 and 1 is for the position based, and for force based it is like exact 1, like because it's like perfectly behaving as an elastic object. Is it something like that?
So in position-based control, actually you can control that. So if you look at the right equation over here, if you put the alpha as 0, it becomes a rigid body.
Okay, so
It's
it
a
can
hard
transfer.
constraint.
Okay.
But if you add some of the value, it becomes a
Deformable.
deformable or like spring like object. Any other questions? No. Okay. Okay, then I will.
Great presentation. Thank you.
And Yifan can take over.
We're good at controlling time. It's been just half an
Very, very
hour.
well controlled,
Exactly
yeah.
half an hour.
I was looking at time while doing the presentation.
Wait, actually. Oh yeah, you guys are seeing my screen right? So there's just oh
You can join through the Zoom and then share.
yeah, okay. So this was directly
Oh, no, no, no.
projecting everything on my
Yes.
no.
Yep.
Do you guys know where the start button is?
The down bottom.
Oh, okay, the first one. It's not the first time using this one. The first. The force. This one.
Yeah.
Sorry, this is my first time using this instead of the Google Slide. So I used to it. Okay. So here today I would like to discuss the topic I want to discuss is sorry.
That screen is the presenters.
What to do with this? Wait, do you guys know how to switch back? I should have just used it.
Share. And
Okay, yeah, that works. So today the topic I want to discuss is robust model predictive control, which is a special type of model predictive control designed to work with cases where you have uncertainties in your dynamics model. So to begin with, I want to provide some background knowledge. So this is like the problem statement for a traditional model predictive control. I think some people probably have already heard of it or used it in like some researches already, but just for the background knowledge, usually in model predictive control, what you are doing is that you're optimizing over the next n step and trying to find a continuous series of n action that is going to optimize your objective in the future. So what the major difference between model predicted control and the regular type of control is that instead of just seeing the immediate next one step, you have like now access to the immediate next n step, which is basically what it's saying here. Because if you look at the objective function of the model predicted control, you can see that it has a summarizing term. And this Q here is representing the cost of each step of each action that you have taken. And this P here is the terminal cost of the results of your nth action. Well, the better way to think about it, if you need an actual concrete example, is like, for instance, you're doing some path optimization problem, and then your cost Q here, like each and individual time step for each action you take, you should compute, for instance, here's the trajectory length from the current, like from the last X point state that you have to the next X point state. So you're computing like how far you have traveled given like the new time step action that you have generated. And the terminal step can be like measuring like after all these n series, what's the final distance from the nth location to the origin point that you want to get to. So this is a way of, instead of like just seeing short-sightedly planning for the next state, you can actually see a far vision from the future. And that's why model predicted control is oftentimes used in obstacle avoidance. That is because you can just check if any of your next n step has been inside an obstacle, and if it is, you can just choose another path. And this is what the optimization is doing. But it's noteworthy that here, like in model predicted control, it's usually combined with constraint. You would have constraints with X, you have constraints with U, and it's noteworthy that you don't just have them for the very first action you take, you must have them for all the actions, all the n actions that you have taken during this entire time series. And what's also, and the XT here, you can see it as an initial location, which is like this is where your plan started, and you are planning for xt plus 1, xt plus 2, all the way to xt plus n. And then your goal here is for your xt plus n to end up in some region of attraction. That's why we have this terminal set xf, and I will talk about the reason why we need that in the next few slides. Well, not direct next few slides, but we'll get to that. So that is the standardized statement of model predicted control, but we know that in most case scenario, if you want to use model predicted control directly in real life application, that is not possibly where you can apply that standard problem statement directly. The reason is listed here, as I mentioned, like this is what we assume our model should be. We have a perfect knowledge of our action or what our next action is going to be given our current state and our action to take. And this will be like going on infinitely with no issue at all. That's what we assume in order for the previous problem statement to work. But however, in the actual daily life, what we'll have is like we could either have some errors in the model that we set up, like we could have some error in the coefficient A or coefficient B. We can have some error in the measurement of this U value or the state value X. All of these will result in that we have a bounded uncertainty at the end of this term. Like this cannot be infinite, or this can be infinite like in some certain applications, but the reason why we assume all noise to be bounded is because if it's not bounded, we won't be able to produce any reasonable solution to it, so we're ignoring it just because we cannot handle it. So for the case that we can possibly find a solution to is like when the W here is strictly bounded, it's within a set, and we can see that still, like even though you only have, for instance, a noise of size 1, you shouldn't expect that your system error just to be 1 in all the future iterations. The reason is that in uncertain system, as suggested here, you would have a compounding error like generated by the coefficient of A times that of the previous noise. So meaning that if you have a certain amount of noise in your system, that would just be larger and larger as you run the system. So the longer time you have it, like reiterating through this dynamic model, the more error, the more deviation will you have from this nominal system. And then you can see that comparing this term where we have the noise with this term that we don't have the noise, the extra part is only the third term. The first two are exactly the same, just as the nominal system. But like in the uncertain system, we have an extra term, which is like the summary effect, the additive effect of all the noise that we can have in the dynamic system. Then that is the reason why we need to generate a new type of control method, which is called a robust control, to handle this effect of additive noise. There's the 4 goals that we have when like designing this robust control variants of model predictive control. The first and most important of all is we must satisfy constraints for all disturbances realizations. If you remember that like in the problem statement, we have a bound for like the x state, we have a bound for the u state. We know in nominal system, we know we can know our like what's our x value and u value directly. So we know like once we have a solution that is always satisfied. But in uncertain system, because now we have a w value, which is we don't know the exact value of, like meaning that if you could possibly think that your x is inside this large x set, but actually the x value plus the effect of the w could actually lead you outside the feasible set. So you will be running in the case that you think your next step is going this way and is under the input limit, but actually you're already capping your full capacity here, and you won't be doing any things similar to what you have pictured. So that is the first thing. We need to figure out a way to satisfy the constraints in the noisy system implicitly. And then secondly, it's also important, we need to find a way to converge to a neighborhood of the origin. This is because, as we all know, like if we have noise in our system, we probably don't have accurate measurements of the current states of the robot, and that way, how do we guarantee that at each time step we're still sort of getting closer to our goal is important. And thirdly, we need a way to optimize the performance, because now if we just look at the old optimization problem, probably should go back to that. Because if we now look at this, if we just directly plug in P and Q here, the measurement of our X, the measurement of U could already have noise inside it. So we need to figure out a way to take out those noises and take out the effect of the disturbances from our optimization. Because first, we don't know what actually the disturbance is, and if we consider them, the optimization will be really, will be less seamless and less continuous, because the noise disturbance themselves can be bouncing back and forth. So that's optimization. And the fourth, we also want to make sure that the method we generated give us a large enough feasible X set, given that the condition 1 and 3 are met. I probably need a wet this one. You can see. Do you have the camera that you can switch to? No, it's not working. Okay, that's okay. But at least you can see. Oh, sorry, I erased it. Does anyone speak? I just have to get a line. So for instance, this is the entirety of the X set. And that you must stay in when like solving the model predictive control, and this is your goal location. And you could also have a limitation on bounded for the U, but in some cases scenario that, like for instance, the model predictive control will realize that only that when your initial time step is within this region, you will be able to only if your initial time step is within this region, you will be able to find a way to go to the terminal set. But however, like this is dependent on how tight your constraint on U and how tight your constraint on X is. So it's a compounding effect. But in certain cases scenario, like especially when we take noise into consideration, a lot of these like constraints will have to be shrinked, and as a result, this initial set that we can end up getting to the ultimate location will be smaller and or largely shrinked. And in certain case scenario, it can also be even an empty set, and we don't want that to happen. So we want a method that can generate an as large a region of X0 as possible. So ideally, maybe the closer to like the full set that we have is the better, instead of just having these two. Because if you think about like, even if we have a solution in this application, but it has a very limited use because you have like such tight constraint on what your initial location X can be. So you might only need to, you can only probably use it in one case or scenario, but in like a small variant of the situation, it will lose its effect. That's why the fourth one is important. And to begin with, I want to talk about how do we construct cost function for the uncertainty system. As you can see, the first line here is the standard cost. I'm sorry for the notation, they are not quite consistent. This is the step cost Q. This is the ultimate cost to terminal cost P. So they're just different notations. As I mentioned earlier, that in the new optimization function, because we don't know what the W or the disturbance value is, we must figure out a way to build an optimization function that is clean of the disturbances. And there's many ways to do that. Like, for instance, you can do minimizing the expected value of this term. Like, just like given, because in this case scenario, you probably would have a probability curve of what W would be, and then you will be able to compute it, the expected value, like which is E bracket the J, given the probability curve of W, and you will be able to find the value. That's one way. And you will also just to be able to do something like minimizing the variance of W, which is minimizing the effect or oscillation that W could have on your ultimate J value. You can also consider the worst case, seeing W as a very smart component that's just deteriorating every effort that you have attempted. And here, there's also the most, but the most common one and the most easy one to do is just assume that this is an ideal system without the effect of the disturbances, which is the one shown here. The goal here is just eliminating the effect of disturbances because we don't know it. And here is a more detailed illustration of how do we enforce constraints for uncertain system. This is definitely a bit better picture than the one I drew over there. So as you can see, we have like, this is the feasible set for X. What we want to do is like, we don't want because like when we are generating trajectory, we don't want any points on the trajectory to go outside the feasible set of X. But however, in the nominal system, we know like our X is just going to be like this solid line here. But when we introduce noise, which is oscillation W, we now, instead of having one fixed point, we would have a region that our next stage could possibly end up with. So it's no longer determined, and we don't actually know where exactly in this region our trajectory will land. So, and that's why when you are enforcing the constraint for uncertain system, you should always make sure that even any points inside this region plus like given the current nominal system location is, you will not go outside the feasible set of X, is what this is trying to do. You see, like the edge must strictly lies inside the feasible overall set. And the idea is just to compute a tighter constraints, given that if the nominal system meets the constraints of like the problem statement, and in that case scenario, well, sorry, if the nominal condition met this like tighter constraint that we have computed, then we know the actual system will meet the constraints listed by the problem. I don't know if that makes sense. Does that make sense? If it's confusing, like you can ask questions, because I it's hard for me to give feedback of how you guys follow along. Okay, but there's two types of robust control methods for model predictive control. One of them is open loop, the other is closed loop. Just to begin with, I want to say that the open loop robust MPC is barely used at all, but it's mentioned in all of the tutorials on like robust MPC because the knowledge, you must understand the open loop robust MPC before you can actually understand the math behind the closed loop more complicated optimization for MPC. But today I will start with the open loop model predictive control in the robust version, and then I will also mention some parts of the closed loop version. But I guess I will probably not be able to finish the entire closed loop discussion. I can continue next time, or if you guys are interested, I can just talk to me after this. So here's the problem formulation for the robust open loop MPC. So for open loop MPC, if you remember like the previous page that I have talked about, like how the noise effect is additive, like as you move along the trajectory. So this is exactly what this term is computing, is the additive effect of the noise on the system. So if you want to visualize it, that's this case scenario. For instance, this is your starting location, and now this is the noise size that you have. And then you move on to the next step. Because of the additive feature of the noise, you will now have a larger noise region. And then in the third step, you will have an even larger noise. This is exaggeration, but you can get the idea. Just saying that as the trajectory or the time steps becomes larger, the trajectory goes on, you will have a larger and larger effect of the noise. That's why you need to take care of them individually given different AIWI. So the AI here is just like these times WI is like it's vertical, so W0, W1, W2, W3. So when you times them, you will get the additive results of the noise so far, and it will just keep increasing as the I value gets larger. That's why, and this specific symbol here is the Minkowski. Well, it's not exactly Minkowski sum. It's doing the minus signs and the plus sign. But I will talk about the Minkowski sum in the next slide. And in the terminal set, we can also see that besides changing just the constraints, we also need to change the definition of the terminal set, because if you remember, this terminal set should be like a region of attraction that the end term must ending in order to guarantee that our model predictive control remains stable. If we don't guarantee that this end term is within this region of traction, we don't guarantee the stability of the model predictive control, so it might not converge. And as a result of the noise, this terminal set has this region of attraction also will shrink definitely under this effect. So that's what I mentioned, like sometimes it can be an infeasible empty set and you will end up in the condition with no solution. And that's the reason why robust open loop model predictive control is barely used. Because you almost always would have like a near infeasible set when the I is large enough. And so for some background knowledge on the math, like the Minkowski sum is like just like doing a geometry summarization of like the two polygons that you have given. Like, so this point here is the 0 point, like and that's why it's only, well, the other can be positive, the other can be negative, but the 0 point must always remain on the edge of the other polygon when you're doing the summarization. So basically that way you're doing Minkowski sum, they would like, in our case of application, it would just show you the compounding geometry region of the oscillation generated by the nodes. And that's what we need to minus given the from the extent constraint. And also, and then also remember that I mentioned that the terminal state XF must be like a robust invariant set. well, in order for it to be a region of traction, it must be a robust invariant set given the noise. And in order to understand what is robust invariant set, here is a definition. So for robust invariant set, it's basically saying that once you are in the set, you will always have a way of staying inside the set. So meaning that you will never go outside the set if you choose not to. And well, that is for the nominal case scenario, but in this case where we have noise, it's a little bit different. It's that it must be a set, well, a robust invariant set will be if you can guarantee that you will have a way of staying inside the set for all possible noises in the noise set. So you need to generate, like, you need to figure out, like, you need to make sure that no matter what the given noise is like you will have a U that will make sure that you stays inside this O set instead of being pushed outside by the noise. So ideally, well, intuitively, we can see that for a set to become a robust invariant set, it's harder than for it just to be an invariant set, common invariant set. So the robust invariant set will be smaller than the common invariant set. I don't know if that makes sense. Because now you need to come back to the effect of the noise, that way it's shrinked. You cannot stay on the edge of the invariant set, because if you're on the edge, the noise could push you off. And this is like some, and then this is how robust invariant set is computed, or any types of invariant set is computed, is using the combination of the preset and the current set. So remember the definition of the robust invariant set is that if you are currently in the set, your next step will never, you could not go outside the set given any W value that you have. So basically this is saying that if your current set is in the robust invariant set and your preset is also in the robust invariant set, then if you take only the combinatory part of this, you can make sure that part is definitely a part of the robust invariant set, and that's how robust invariant set is computed. So for instance, you have the state X. This is your current step, and then you need to compute its pre-step. The pre-step could be something, I'm just drawing like randomly. The pre-step could be something like this. This is the pre-X. And then, so you know, like these regions cannot be like inside the robust invariant set because the pre-step doesn't equal to the current set. Like these are the feasible candidates, but this is not done yet. You need to run this iteratively, and then you compute. You see the second set that I just drew, the smaller one, as the current set, and then you need another preset. This is the preset, and then these are no longer considered as part of the robust invariant set. Only like when the preset and the current set like exactly are equal to each other, you can stop, and then you can see what you have right now is like considered as a robust invariant set, meaning that no matter how many times you trace back to the preset, you will always be in this set. Or no matter how many times you push forward to the future step, you will always be in this set. So that's the invariant set. And this is the knowledge of the preset. The preset is just if it's a preset, it's guaranteed that it will be able to find a way to get into the next step for all the W that you have. Yes. And then this is just an illustration of the contradiction between the nominal invariant set and the robust invariant set, just so you guys can see the shrinking effect. Because when you're just computing the regular invariant set, when you're computing the preset, like this W will essentially be 0, so you don't need to minus W out from like your left side. But when you have robust invariant set, you actually need to do that. That shrinks the size of the terminal region that you found. Okay, and so that is for the open loop model predictive control. Does anyone have any questions? That it is clear. And here's some of the weaknesses of robust open loop model predictive control. As we said earlier, this additive effect of the AIWI, it can end up be really large. Well, will have something to do with the eigenvalue for A, because if your eigenvalue for A is larger than 1, you can see that it will definitely have an enlarging effect of bouncing, of making this W say if your eigenvalue is 2, then the W size will be twice larger than before, and it will keep going on until it becomes indefinitely large. So in those case scenario, this open loop solution would definitely be infeasible for sure. That's why it's not very useful, because in most cases we cannot guarantee that in all of the applications that we are using this method, the A always have eigenvalues smaller than 1, meaning that it will not enlarge the effect of the W. Well, and the solution that has came out is that robust closed loop MPC. Now, instead of if you think about the open loop, is that the agent is doing its own thing regardless what the disturbances has done to the agent. But in the actual game, this is sort of related to game theory. When you're actually playing a game, imagine that the disturbances is your opponent. In your current time step, you actually have knowledge of what the disturbances has done in the previous time step. You cannot predict what it will do next, but you have you have your current state. So you probably know what's the effect of disturbances over the history step. And you can actually have some control policy design in response to that instead of just letting it grow blindly. So that's why the closed loop method has come up. There are many variants of the closed loop methods but the most popular one and the widely used one is the tube MPC. Probably someone has also have heard of this. It should be used in a lot of different applications. But what the tube MPC does, it's there's a lot of math behind, but in general, if you want to know what the tube MPC does, it is separating the control system of the agent into 2 different sections. The Z section, which is the nominal section, and then so in the Z controller do not take into consideration of anything related to the disturbances. It just do its nominal system thing instead of considering the fact that it's actually have noise deteriorating its performance, because it has its teammates, the E component, which will take care of which will be the player 1 and player 2 fighting with disturbances, and this controller will specifically be responsible for shrinking and eliminating the arrow from growing too large. And then you will be able to, instead of having a growing size of the noise region, now this time you will be able to have it as a fixed size region. So it will not grow over the process and become indefinitely large. And this is the mass for the nominal system. As you can see here, instead of X, we're using Z just to differentiate. Whenever you see Z, it means it's noise-free and the accurate measurement. So now this is a nominal, and then for our controller, we actually this V here is the controller U that is control the nominal system. So here instead the actual control policy of the new agent that we designed consists of the nominal controller, the V from the previous nominal system, and then it also have a new part that is taking care of the differences between the actual current state to the nominal state. And then if you do some math, using E to present Xi minus Ci, and then plug in the Xi plus 1, use a dynamic system for Xi plus 1, and then plug in the dynamic system for Zi plus 1, you can actually find that the Ei plus 1 is actually determined by this effect. And in this specific effect, the A is the coefficient, the B is the coefficient, but we have our choice. We can freely choose what the K is, and therefore we can have a limitation on the size of the noise region. Yeah, so that was what's said earlier here. As you can see, instead of having the AIWI term that's become increasingly large over the time step, now you have a fixed sized region that is just epsilon, whatever it is, and then you can just it would not increase as the system keeps on running. It would just stays the same, and that way you have you can almost always guarantee the feasibility of your system without it to expand too large and render the problem infeasible. And like the robust open loop, it also you need to make sure that the constraints for the new set and the constraint of the old set is shrinked properly to prevent it from actually going outside the feasible limit that you have set. This part, the constraint part, is exactly the same as the open loop section of the model predictive control. And then for the cost function, likewise, you are just ignoring all the effects of the W. You're just taking into consideration of only the nominal system. And then you're optimizing over it. And this is the ultimate control law, which is the same as the previous page. Yes, that should be it. Strange areas, what else is supposed to be?
Just stop the discussion.
How
did you stop the?
I'm not quite sure, but we can do that. I don't think I stopped it, or did I? Okay. Yeah. Wait, actually, I want to show you guys an image of the tube MPC. Oh yeah, this one. So this is what tube MPC will look like in effect, because you can see that the noise size. Consider because you already pick a K, that your noise this is more. It has more mass. Like this region is actually computed as is also like a form of robust invariant. Instead, you must compute this offline and before you run online for the actual optimization process. And then you're also choosing your K offline. You have to choose your K first, and then you can compute the size of this region, and then you run it online to get a convergence curve. This is what it looks like. But the good thing about using a closed loop method now is that your region because this is computed offline, it will be fixed forever, and the effect on noise under the control of the K x minus C term will never go outside this region. Yeah.
Is there any problem with fixing the K in offline?
Fixing the K in offline memory?
How do you decide the K?
Yeah.
What is the possible limitation of fixing the K?
Well, there's actually a lot of limitation in fixing the K because you can see. Because if you can see the K, there's two parts where the K is taking effect. It is here, in the feasible set for the U, in the shrinked feasible set for the V, but it's also invisibly embedded inside this epsilon set. So the reason for the K is if you pick it to be too large, your feasible set for U will be very, very small. But then if you don't pick it to be large enough, your epsilon will be really, really large. So that's the tricky part when it comes to computing K. So computing K is actually not as simple because today I don't want to go too deep into the math, but it's actually not as simple as it sounds. But you have to make a good choice between like whether you want more like action control or you want to have like smaller region of the oscillation for noise.
I have another question.
Yeah.
This is just general question about MPC, but how do you choose the horizons?
That is a really tricky question because most people
Because with this two MPC or this open
Uh-huh.
node MPC, it seems
Yeah.
like choosing a horizon is harder than before. So I was just curious.
Well, when you're choosing usually there's common. Well, most people would go with 3, 5, 10, but usually few people would go beyond 20. I would say that intuitively. Not also it depends on your application. Depends on what you want to do. For instance, if you remember from my qual presentation, I was trying to use it to do obstacle avoidance. But in the case that your geometry is really weird, you would have to have a really large, future vision in order to bypass that. But if you are not using this for obstacle avoidance, it's also very application specific. Yeah, but the general idea behind it is you probably don't want to make this n too large because usually if you try it for 10, 5, it's sufficient. It should be sufficiently well for most application scenario. If you're not dealing with like obstacle avoidance or too complicated a system. The reason why we want the value of n matter is because that for instance, this is the feasible set. The reason why n matters because if this is x0, if you say the n is 2, your n could go here. And then at this edge, you will find there's no you can actually push it back in this way. It will have to become infeasible in the next step. So the larger vision you have, like the clear idea, you will be able to guarantee all your future set stays with a feasible set. That's also what the terminal cost here is trying to do, because if you have a terminal cost, if you are able to guarantee, for example, this is the robust, the invariant set for the XF, if you remember, that's the terminal set. If you're able to guarantee that the end of your n goes into this region of attraction, you can guarantee that it will always stay feasible. That's why with a proper XF, we are able to choose a smaller n size, smaller step size for a lot of potential. But in the case you don't actually have a good enough terminal set, that region of attraction, or it's extremely small and impossible to get into, you would probably go for a larger horizon value.
Because especially with this open loop case,
Yeah.
you have extremely small.
Yeah, right.
terminal
That's the issue.
set. So like.
But if you don't make it large enough, it probably won't even be able to get to the set that you
Yeah,
designed.
so
Yeah.
then the number of horizon just really matters.
Right.
So I
Right.
was curious.
So it's like if you don't make it large enough, you probably won't be able to have xn going to the xf at all. But if
Yeah,
you make it
that's
too large, you see that this is
will
making
increase.
this
Yeah.
almost disappearing.
Yeah.
That's tricky. Yeah, but so that's why it's good practice to always have like an XF design for your case there. It would definitely speed up the convergence and enable you to work around with like really small n value. And do you have it? Yes.
So my first question is disturbance.
Yeah.
You know, the disturbance variable can be treated as a variable with its own dynamics, or is just a random variable with
In
one-
this
with its own-
discussion, we are assuming it's all random. Because we're here in the math behind, we're not assuming any dynamics of the W. It can actually have dynamics, and then that's when you use like Kuhlmann filter or any other type of filter to do the noise estimation.
So it is just a random variable which has
Yeah.
specific
Yeah.
like Gaussian.
Yeah, it just there's no limitation on what type of like this figure.
And actually in MPC you're just considering several steps ahead of the current
Right.
state.
Right.
So there's another control algorithm which is LQR.
LQR, okay.
It is considering the infinite time.
Mm-hmm.
So
Well, actually, I
Right.
think LQR Well, it's considering infinite time, but in real application, I don't think is it actually using the infinite time horizon to solve problem?
I don't know, but in my understanding,
Okay.
why we are using MPC instead of LQR is that
Uh-huh.
MPC is better at dealing with constraints,
Mhm.
right? Am I right? Just wanna.
Yeah, I think so. LQR, if you want to use the very simple, very fast algorithm to solve it, it cannot have constraint as far as I remember. But I don't take it for sure. I think
for
it does.
LQR they have analytical solution
Yes.
of every time.
Right.
So.
But
it's
that's when
impossible
I
to-
think that's when it doesn't have constraint and it has to stick very strict to its problem statement. Like model predictive control is like the way you can actually use it to handle more complicated system and constraints. But I don't think I think the runtime for model predictive control, because it can be solved using a batch approach, which is sufficiently fast even if it's enforcing linear constraints. As far as I remember.
That has closed form solutions, batch.
But I don't know if I should just call that batch closed form solution. I don't think it's closed form. No, it's not closed form. Wait, actually, is it closed form? Well, it's not closed form if you have constraints. If you don't have constraint, that's closed form too. Because if you have constraint, you're essentially plugging that into a QP problem. So that turns MPC into a QP.
Yes. And last question, probably stupid, but what if the dynamics of the system is not linear? What if it's not linear system?
Well, if
Then
it's
you can't get the AXI.
if it's linear, you can just do an approximation and then make it linear.
Yeah, I mean,
Because in
this is the
computation
problem.
wise,
That's the problem.
Yeah.
Because you're predicting the model.
Right.
So linearization might be impossible.
right, that's true.
Because linearization is just on one point.
Yeah,
So
maybe you can do multiple linearization and then piecewise linearization.
piecewise linear, yes.
Yeah, just the computational wise, having a linear system is so much faster than if you have a more complicated system. In a more
Yeah.
complicated system, you want the current batch, the simple batch approach solution to the MPC will not work. So it's best that you stick to linear if you
I
want.
think linear approximation is okay in this case because there are already constraints and noises. So we can consider the model model differences in noise.
I don't know, probably. Well, that's an idea, right?
In this case application, I actually.
I think
Well,
you're
because
right.
open loop itself is a weak method, so I cannot guarantee that linearization will work. But let me see.
That's true.
If it's tube, it should work fine because now here everything is exact. I'm assuming if you do the approximation good enough, it should. Well, because if one approximation is not good, you can try the piecewise method, like using multiple linear instead of just.
If the frequency is too high and if we are making, it is not something we do like approximation at every step, like at every delta t.
Yeah.
Then it can be a closer approximation to what you're trying to do because the frequency is very high. Like how much can you do in 1 millisecond or 1 microsecond? Like how much can the model behave erratically?
But I don't think I recommend it changing it real time, changing the linear system real time. I don't think that. That
Yeah, I
probably
don't
will
think that
be.
it is happening.
Yeah, that will
at
be
every step.
computation.
Yeah, it does not happen at every step.
Yeah.
But I think Hoji's idea is really nice. You can treat the distance between the real system and the linearized system as disturbance. And probably,
We'll just formulate it as a nonlinear system and do a nonlinear.
Well, but then that disturbance is also growing if you the further you are from the point that you selected for linearization. It could I don't know how large it can go. It maybe will also be indefinite because we don't want it to be too large.
Yeah.
If the noise becomes too large, everything here will be infeasible. This will be an empty set. This will be an empty set. Then we are not solving anything at all.
Yeah, and especially if you have a longer horizon.
Yeah.
going to become a disaster.
Well, the good thing for two-band PC is that now if you are using a lot, well, it's not as bad as if you're using an open loop, so you can actually you can try a longer. At least the noise side here won't be any larger. So I don't think I think horizon here is not as sensitive as in the open case scenario.
I
Yeah.
guess.
So if you want to go with you need a larger horizon, try this. But actually, always use the closed form. Don't ever go to the open form, open loop.
Yeah.
It's bad.
Designer K is very important.
Yeah, designer K can be a separate lecture of its own.
Yeah.
I have a very quick question. I'm kind of confused about
Yes.
Minkowski sum and difference. Are they completely reversible processes or not?
I think they're completely reversible. Yes.
Because I remember Murari saying that. I mean, the difference.
He said it's not reversible.
Yeah,
Really?
I think so, and I mean that is what he said. I tried running it there, and I'm not very sure about the results.
I'm pretty confident, at least in
Because
all
the
of the
geometric
applications
additions.
here. At least in all of the application here, it's inversible because I remember like in all the previous slides, he was doing like epsilon plus z belongs to x, and then like in the actual problem statement, it's able to minus it back. So I see both type of way of writing it in his slide. So I'm sure at least for this case scenario, it should be inversible.
I also think so because
Yeah.
like one polyhedron
Otherwise,
subtracting another
You
set.
won't be able to write it in this problem statement. You will have to do epsilon plus the I belongs to x. But they're able to write it back in this form because it's inversible. That's what I think.
Right, it should be inverse because I remember like someone was asking in the exam citation that the Ponti-Raggin difference and Minkowski sum are reversible or not. And I think Murari said no to that. I think so.
Okay. I don't have that part of
I
memory.
tried running it.
Yeah.
I'll have to check it again.
Okay. But at least I think here in this problem setting, you can use it. Yeah. Is there any other questions? Yeah, that will be all for the Tuesday.
Last one was also great. Last one fresh. Food was also good.